My name is Damien Chua, and I'm a scientist at the Naval Research Lab here in DC. And I work in the Space Science Division in the solar physics branch. So most of my work right now is relating to understanding the sun and how it affects the space environment around the Earth. In this presentation, when Patrick and I kind of scoped out this talk and what the interests were of the group, I tried to kind of gear it toward space weather effects that are relevant to HF radio communications, which of course involve variations in the ionosphere and regions of space that are a little bit closer to us. So hopefully that's what we'll see tonight. So in terms of what we call space weather, it's really kind of analogous to understanding weather in general, or how we understand weather near the ground in the troposphere. But I just wanted to reference a couple of things that have happened over the last, say, 20 or 25 years. So I don't know if any of you remember this, but back in March of 1989, there was a huge power grid disruption in Quebec. In fact, there were about 6 million customers on the Hydro-Quebec grid that were affected by this for an extended period of time, over 9 hours. I think this extended down into the eastern parts of the US as well. So that's one event that we sort of point to. Also, a little bit more recently, in October 2003, the FAA's Wide Area Augmentation System, which is a guidance system used meant to augment GPS navigation, was brought down for a period of about 11 hours during a geomagnetic storm. If you were flying in a plane anywhere over CONUS, the plane would have had to have reverted back to older navigation systems to guide their approach into whatever airport they were going into. The next example I show here was a little bit dated, January 2005. I'm sure there are more examples that are more recent, but it's difficult to get information like this out of airlines because these are operational details and they're sort of loath to share them. But in January 2005, and you'll note this is sort of during the peak of the last solar cycle, there were 26 flights that were diverted from polar routes going over the poles because of high latitude HF radio blackouts. And this is a big deal because the reason why you fly over a polar route or over the poles is to save you a lot of time and gas, jet fuel, flying from places like from Chicago to Beijing, for example. And if you can't fly over the poles, you're incurring a huge operational hit in terms of time and money. A little bit more serious example down at the bottom, during the Battle of Takur Ghar, during Operation Anaconda in Afghanistan in March 2002, there was a fairly serious UHF-VHF SATCOM outage during the forensics of that event. It was thought that there was a significant ionospheric contribution to this. So what do all these things have in common? Well, all of these events are related to the variations both in the ionized portion of our atmosphere, or the ionosphere, and all these things are also tied to events that originate at the sun. So this is what we're going to talk about tonight, and hopefully we'll be able to give you some insight into the degree of the variability, what kinds of variability that we see, both in terms of the time scales, but also the spatial variability that we see. So, as a general outline for the presentation, I thought I would kind of organize it by starting local and then expanding out. So effects that you see are kind of on the local horizon. So where you're standing, if you're sitting on the ground with your transmitter, you know, what kinds of effects and phenomena you'll experience. We'll sort of extend that by broadening that to over the horizon into a slightly larger domain, and then extend that to the global ionosphere and talk about the structure of the ionosphere globally and how it varies. And then we'll keep going further out and try to tie that to the drivers of that variability that originate out further out in space. So this would include things that happen out in the Earth's magnetosphere and then ultimately at the sun. So just to back up, I'm sure there's, you know, you can see some math here, but I really didn't intend this to be a super technical or quantitative. You can tell me if this is sort of old hat to how you understand the ionosphere. But I just wanted to go back and just sort of refresh. You know, basically, if you send up a radio wave from the ground, you know, why does it reflect? I guess it's fairly common. It's sort of a basic phenomenon, especially to a radio operator, that you broadcast a radio wave and it reflects off a portion of the ionosphere. But I thought it'd be useful just to go back and go through the basic physics of why that happens. So the ionosphere, of course, is the ionized portion of our upper atmosphere where there are this mixture of free charges, ions and electrons, electrically neutral, but there are free charges up there nonetheless, and this overlaps with the upper parts of the neutral atmosphere. And you know, one way to characterize the ionosphere is by this parameter called the plasma frequency. And this is just the frequency at which say that the electrons or the ions oscillate up there due to, say you take a bunch of electrons and you perturb it, well, you leave a positive charge and it's void, so which attracts electrons back toward that space. And it sets up this oscillation, and without any other forces to damp that, you get this oscillation that's proportional to the density of the electrons up there. So this is sort of a basic parameter in the ionosphere. And so if you send up a radio wave up the ionosphere, its propagation is dictated somewhat, or mostly by the index of refraction in that medium. So if you think of it as you can think of it as in an analogous way to just a light wave propagating through some medium, and the medium has some index of refraction that dictates the path of that wave. So if you send up a wave with a frequency, some radio transmission with a frequency much higher than the plasma frequency, then the ionosphere is essentially transparent to it. The radio wave propagates straight through. So so FM radio broadcasts, fairly local kind of thing, because 100 megahertz, you're basically transmitting through, and those wavefronts are going to propagate through most of the ionosphere. This is of course a fairly first order treatment of the whole situation. So and then as the frequency approaches the plasma frequency, the index of refraction starts to decrease as it approaches zero. The wave starts to the group velocity of the wave approaches zero. And then as we get to the critical frequency, where the frequency equals the plasma frequency of the medium, that's when we get reflection of the radio wave. And the radio wave is reflected back down. So in terms of, so there's the relation, there's a direct relation then between the frequency of your wave and the density in the medium, in the ionosphere. So that kind of dictates where, at what altitude your you're going to experience that reflection. Just to make that connection a little bit more clear, so on this plot here, I'm showing the plasma frequency on the x-axis and then the corresponding density of the plasma at which that critical frequency is experienced. So I'm just calling out here a couple of frequencies that are commonly used in the amateur radio community, and you can sort of map out exactly at what density that critical frequency will basically where that occurs. So you can then kind of map this out as to the regions of the ionosphere where you find that. So this principle, in fact, was how the ionosphere was discovered in the first place, back in the early 1920s, I believe. They started experimenting with RF propagation in the atmosphere, and this technique is still used today. You have an instrument called an ionoson, which is essentially a fairly simple HF radar, essentially. They operate between about 0.5 and 30 megahertz, typically using powers of around 200 watts. And they basically just send up RF up to the ionosphere and they sweep through these frequencies and they see at what frequency they get the return. So you get plots like this called ionograms, where here on the x-axis is plotted frequency in megahertz, and this is altitude. And so the modern digital ionosons, they sweep through, and they get the returns, and they basically map out where those returns, during the time of flight of the radio wave, map out at what altitude they get the return, and they're able to basically plot out what the altitude profile of the ionosphere above the site looks like. So so that produces a typical ionosphere profile like this, where on the x-axis is the electron density in electrons per cubic centimeter, and then altitude. So you can see there are a couple of plots here that show both what the ionosphere looks like during the daytime, which is this solid line here, and then what it looks like during the night. So you can see a fairly drastic difference between the day and night ionosphere. The dashed lines correspond to, the solid line corresponds to a solar maximum condition, and then the dashed lines correspond to what it looks like during a solar minimum condition. So variability shown here, both on we see the diurnal variability of the ionosphere, and also the longer term 11-year solar cycle variability. So quite a difference between solar max and solar min. Even within the daytime, there are about 2 orders of magnitude different, 1 or 2 orders of magnitude difference in the electron densities. So those are the sort of temporal variations that we see on daily and solar cycle time scales. Now, what about how the ionosphere varies spatially? So this is a representation of the map of the global distribution of electron density. You can collapse that into a single parameter called the total electron content. So blue is low, of course, red is high. You can see the day-night terminator shown here on this map. It's a little bit hard to see on the display, but obviously day-side ionosphere, where the ionosphere is fairly dense. The day-side ionosphere is supported by most of the production is just essentially by photoionization. Solar UV and far UV light creates photoelectrons in the upper atmosphere that populate everything from the mostly the E to the F region. But you'll also see, aside from that sort of zero-width order structure, there are you'll see a couple bands that kind of parallel the magnetic equator, and you'll see that they actually extend out further past the day-night terminator. And this structure is known as the Appleton anomalies, or the equatorial anomalies. And you can understand these. You would think that once you remove the sun, that you basically remove your source, your production, and once you do that, most of in the night side ionosphere, you would expect most of that to go away. Once you have free electrons, there's a process called recombination, which removes those when they interact and become neutral again. Or you just turn off the source, which is the sun. But at night, in particularly at higher altitudes where the recombination is weaker, there is an effect called the fountain effect, where the night side F region ionosphere is supported by basically transport. You're taking electrons from the day side, and because of the prevalent configuration of the electric and magnetic fields, plasma is brought up along magnetic field lines, and at night they start to settle, and you get these two peaks of ionization called equatorial or Appleton anomalies that persist throughout most of the night. So this diagram tries to show this a little bit in a little bit more of a context of what happens relative to RF communication. So the presence of these anomalies at night just presents another structure upon which radio waves can reflect. So it's another ionospheric phenomenon that is present, sort of ubiquitous among throughout the night, that is present, that can affect radio transmission as well. This is what they look like in actuality, so that going from sort of a diagram to real data. These are measurements from an experiment that I worked on called SULI, which is actually an optical instrument, but it uses far ultraviolet emissions and inverts them, if you know the process of how those emissions were created. And you can do essentially like a tomographic inversion to infer what the electron densities are.
Question.
So, yes?
I can't read correctly. So what are the axes?
So this is magnetic latitude. So the center of this plot is the magnetic equator.
Okay.
And it goes from about -50 to +50 magnetic latitude.
Okay.
It's such a single cut through the ionosphere. The instrument's viewing along the track of a single satellite, and it's scanning in altitude, which is what lets us...
so what's the vertical axis?
Vertical axis is altitude from 100 to 800 kilometers.
Okay, okay.
And the colors represent electron density.
Okay, fine.
Yeah.
Thank you.
How do the altitude compare with the orbits of various satellites, the ISS, Space Shuttle, or GPS satellites?
Right, so this particular satellite is orbiting at an altitude of about 500 to 600 kilometers. The ISS, Space Shuttle, are at an orbit of about 350, I think.
So they're right in the middle of this.
Exactly, yeah. So they're, the inclination of the ISS orbit is such that it probably passes through some of these, but for the most part.
Minimum altitude for satellite orbit is about 100 miles.
Yeah, that's right. And so this is just showing. The intent of showing was to show that there's fairly irregular structure to these, and I'll show some stuff that'll show that there's even finer scale structure yet to what we see in the ionosphere. The bottom plot is essentially just a comparison to an ionospheric model that sort of gave us a little bit of ground truth to our observations. So the scale size of these, they typically extend about 10 degrees in magnetic latitude, and they can extend in altitude for, they have a scale size vertically of 100, 200 kilometers. And like I said, they extend out across, basically from, they start out at the day side and they extend out through the dusk and the night side region. So this is another view of what they look like in actual observations. The equatorial anomalies, you can see that they basically parallel, they track the magnetic equator, which is shown by this line here. These are observations from a satellite called Timed. It has an ultraviolet imager, and it's also in low Earth orbit, so you can see it's taking these swaths of data across the night side. The one thing I wanted to point out here is that embedded among the larger scale structure of the Appleton anomalies are these little striations, these depletions of plasma. So the intensity scale here is proportional to the concentration of electrons. If you look at this in a little bit more detail, you can see that there are these sort of tendril-like structures that have scale sizes down to a few tens of kilometers. And we're getting a better understanding of the occurrence of these, called plasma bubbles, essentially. They're local depletions of plasma that can have fairly serious effects on RF propagation. Essentially, anytime you have a strong gradient in the electron density, so either the outside of these regions, the Appleton anomaly regions, or within them, and if you experience a strong gradient across that that index of refraction that I mentioned before in previous couple slides ago is going to change dramatically at that boundary. And of course, when you have a large change in the index of refraction of your radio wave, you're going to have experience issues like scintillation, or it's not going to propagate the same way that it was before it encounters a structure like this. So this is about a 90% depletion typically in these plasma bubbles, and you can see that they occur fairly across a fair amount of the night side ionosphere, and they're caused by essentially by the same process that happens when you put a heavier fluid over a lighter fluid. The Rayleigh-Taylor instability is what it's called. You have transport that somehow puts a denser fluid above a lighter one, and they typically, what it wants to do is they want to switch. So during that process of transport vertically, you get these voids, and as a result, we observe these depletions in the night side ionosphere. So if you're trying to transmit a radio wave through that.
The picture on the left is showing horizontal depletion, not vertical, right?
That's right. So it's a little bit. So this is looking. It's the instrument's observing down. So this is sort of a 2D image looking downward. But actually, the image that I'm showing here on the bottom right is a simulation of these plasma bubbles in altitude.
I mean,
So
to the side, and that's what we're seeing.
right, yeah. So this is looking at it from the bottom, and this is sort of looking at it sort of edge on. So they do extend in altitude as well. So that it's, I haven't really seen a very good sort of 3D reconstruction of one of these bubbles yet, but this sort of gives you a sense of how they're structured.
Do they have some data for 3D, or is
It's
do not have that yet?
it's possible to do. You just have to have the right observations to do it. You can do it tomographically through, if you have, so these are from all sky images. It's basically like a fisheye lens on the ground. If you had something that's scanning from the other direction, you could reconstruct it fairly well, I think. The models and the techniques are there. It's kind of like when you go get a CAT scan. It's basically the same tomographic technique. So, but like I said, these plasma bubbles, they have scale sizes ranging from, say, 100 kilometers down to a few tens of kilometers. And I think we're also starting to see, as the observations get better, that maybe the scales go down even smaller than that. Going back to that event that I mentioned at the top of the presentation, March 2002, during in Afghanistan, during Operation Anaconda, there was a Chinook that was dispatched with a team of Army Rangers up to a mountaintop to rescue a group of Navy SEALs that were trapped on top of the mountain. A transmission was sent to that helicopter telling them not to land at the location where the SEALs were, because there was a significant enemy presence at the time. That helicopter never received that transmission, and there was significant casualties associated with that helicopter continuing on its path. And during the forensic analysis of that event, there were some ionospheric scientists who went back to see if these plasma bubbles had anything to do with that. So military SATCOM, usually I think they operate around the 240, 250 megahertz band. And it was, the study concluded that it was a combination of multipath, so it's a fairly mountainous region, a lot of terrain to deal with. But also, there was an analysis of ionospheric data during that day as well. And using data from the same experiment that produced that map, they were able to reconstruct what the ionosphere looked like above Afghanistan during that day. And they actually found that there was a significant plasma bubble directly above that mountaintop. And the study concluded that these plasma bubbles were in part responsible for why the SATCOMs were out at that location during that particular time of day. So it's one example of the impacts of these effects. So these are very...
Did you say that they were transmitting around 250 megacycles?
That's right. That's the frequency at which. Yeah.
Would that normally be a line of sight band, or and was there signal, or if it was line of sight, was there signal affected even though it was line of sight, or do you know if it was?
Line of sight to the satellite.
Line of sight to the satellite, right?
Oh.
There.
Oh, okay.
So they looked at sort of the time history of this event, and the next day when these plasma bubbles were not present above that region, there weren't any issues with SATCOM. I think there were actually other airplanes operating at higher altitudes during that time that also did not experience this. But the combination of multipath and this ionospheric phenomenon, I think, contributed to the breakdown of communication at this particular location and time. So just showing this as one concrete example of some effects of the ionosphere on RF. I mentioned also at the top of the presentation that ionospheric variability also affects navigation. I mentioned that outage of the wide area augmentation system, so this is that example. GPS, people trying to understand variations in the ionosphere and how it affects GPS is a really big topic. As you can imagine, there are a huge number of stakeholders wanting to understand how their GPS measurements are affected by space weather and ionospheric variability. This is one example that's often cited as far as how that affects, say, civil navigation. So there was a big storm, geomagnetic storm, in October 2003, sort of colloquially known as the Halloween storm. And during that time, at the bottom three panels here, this is a map of vertical ionospheric electron density, or total electron content over the continental United States. And as you can see, as there's this perturbation of the electron density that crept further up, further north from the south here, from the equator. And following that, and this is the top three panels here show this parameter called the vertical protection level. So low is good. It means that you can know your vertical position within the network to a smaller degree of higher degree of accuracy, meaning that your delta, your plus or minus, your error is small. And that's what this is sort of normal. And as the event kind of crept up through continental United States, you can see this parameter getting progressively worse and worse. So it was essentially out over the U.S. for continental U.S. for most of the day here. I think in 2011 they did some upgrades, which I don't know the details of, but I understand they're starting to address this problem in part due to this event.
So it's because of wide area, but if you use like deep GPS, differential GPS for that.
Yeah, right. So dual frequency GPS certainly helps to alleviate some of the problems. Single frequency GPS is more prone to variability in the ionosphere for sure. I'm not a GPS specialist, so but I do know that dual frequency is one reason why you use it is it's less prone to the errors incurred by a single frequency receiver through the ionosphere. I wanted to go back and kind of demonstrate on sort of both short and long time scales, what the variability in the ionosphere really looks like. Going back to these profiles of altitude profiles of electron density. When I was still working this program, the SULI program, as I mentioned, it's a UV sensor on board an Air Force satellite, the DMSP satellite, and it takes observations on a daily basis of the ionosphere. And in the orbit that it's in, it creates these altitude profiles of the electron density. That's essentially what you're getting. So this color scale is actually in terms of brightness. It's the brightness of the emission that's used to infer this. But you can think of it essentially as proportional to the electron density. And so what I'm showing you here is, again, altitude. And you can think of each slice along this plot as being essentially this electron density profile coming out of the screen. The x-axis here is one slice per day from January 1, 2010 through, this is in day of year 124 in 2012, so that's like April-ish, I guess. But this spans a couple years. This is essentially 1 year's worth of data here. And what you can see for each day There's a fairly high degree of variability just even within, say, one season. But you can see the ionosphere progressively getting brighter during, even between 2010 and 2012 as we start to approach the peak of the current solar cycle now. You'll also notice that during the spring, the ionosphere is a little brighter as well, or a little bit more active than during the solstice seasons. And I believe that effect has to do with the orientation of the Earth's magnetic field and all the effects of the space environment caused by that. And there's a lot of shorter timescale variations that are represented in this plot as well. So just wanted to give you a flavor of all the different timescales of variability that we see in the equatorial ionosphere. And of course the variability is driven by a whole host of mechanisms and effects. The purpose of showing this is not really to go through each one, but just sort of to convey the fact that it's a really complex system. There are, of course, different physics when you go from the equator up to the polar regions, where you have the auroral contributions to the ionospheric structure. But all of this, again, is ultimately tied to what happens further out in space. So just to sort of go through that whole chain of events connecting the variability that we see here on Earth to what happens in space, I just wanted to show this this little animation that now takes us a little bit further out, really all the way to the sun, but just as an overview of the rest of the talk. You can see that represented here is this disturbance. You can see this large bubble of gas leaving the sun. These, of course, are events called coronal mass ejections. They propagate out through interplanetary space, and then the ones that arrive at Earth significantly disturb the Earth's magnetosphere and drive a lot of, essentially, plasma transport. All the plasma within the Earth's magnetosphere experiences a large-scale redistribution, mainly due to electric fields that are imposed, but also just the mechanical energy that's transported, the mechanical and magnetic energy that's transported out through the solar wind and that hits the Earth. So we'll step back and let's start out at the sun. So these are observations from one of our, well, actually technically two of our instruments on the NASA stereo mission. So these are two spacecraft that are out at the same orbit as Earth, but one of them is ahead of the Earth and one of them is trailing the Earth. So relative to the sun, they're at the same distance at the Earth, but they're kind of clocked slightly ahead and slightly behind. And one of the instruments is the Core 2 coronagraph. So the sun is hidden behind this occulting disk, which is blocking the bright disk of the sun. And this allows us to see the more faint emissions coming from the solar corona. And you can see these periodic bursts of plasma from the sun. And these are like coronal mass ejections that we're so interested in as really the primary drivers of all this variability that we see here at Earth. We're starting to realize that it basically all starts there. So you see these coming off of the solar limb here as these large explosions of gas. And these have scale sizes of essentially, once they get out to Earth, they have the scale size of most of, they expand out and expand out to solar system scale sizes. You may have seen this display before. this is output from a model called the WSA Enlil model. This is used sort of one of the tools used by NOAA's Space Weather Prediction Center. And this is really to illustrate the structure of the solar wind as it propagates out. So in this display here, this is the ecliptic plane of the solar system. The sun is at the center. And you can see this pinwheel pattern of the solar wind going out, essentially, as the sun rotates. This is electron density, again, in electrons per cubic centimeter. The Earth orbit is here. And you can see in this model simulation, and this is based on real data, so it's not just a complete fiction, but it's a simulation of the solar wind. And you can see this periodic, this event here where the model captures this coronal mass ejection as it expands out from the sun. Occasionally these things, when they hit Earth, that's when things get exciting, and that's when we have these space weather events. This is essentially the same display but rotated in the opposite plane. So now you're in the ecliptic and you're looking out at different solar latitudes. So this is the off-ecliptic display. So this gives you a sense of what the system looks like sort of on a grand scale, the solar scale. Advances in imaging have come far enough where we can actually see the solar wind. And this is from a pair of instruments on the stereo satellites that are looking out at the sun from vantage points ahead and behind the Earth. And this is the one from behind, and this is the view from ahead of the Earth. And the sun is located somewhere near the center of this display. What you're seeing here is these faint wisps of gas moving out. That's the actual solar wind, and I think it's. I love showing this picture because I just think it's remarkable that given the densities involved and the background against which you're trying to measure or image these structures, that we can actually do it now.
What waveband is imaging?
So these are in the visible. These are in from roughly, let's say, about 400 to 800 nanometers. That's about the bandpass of these instruments. It's broadband white light imaging, but you're picking out a signal that's about 1 part in 1,000 in the scene. So most of the scene's dominated by basically the visible solar light. As you move out away from the sun, most of it's scattering off of dust. So that's the zodiacal light. So that's most of it. And what we're trying to pick out here is about 1 part in 1,000 on that scene.
Is there some process being used to suppress the background light in these images?
No, this is all just essentially background subtraction. You can't really see it because the field of view, it doesn't include the sun, but we're capturing the background, and the structure of the background is known well enough that you can subtract it out.
Subtracting out the background.
Right, exactly, yeah. So what's left is associated with the plasma of the solar wind, and these, you're looking at electron densities of about 1 to 10 electrons per cubic centimeter here. And this has been a really great tool to allow us to actually see this stuff coming. In this previous diagram, we kind of know when there's some enhanced level of solar activity, and generally speaking how it propagates out through space, and generally speaking when it might reach us here on Earth. But with instruments like this, we can actually watch it propagate out and have a better sense of how fast it's moving, how much density it's carrying and such. So we can actually start to see it and track it as it moves from the sun to the Earth. So moving closer, then now when this stuff reaches Earth, this is a representation of the Earth's magnetosphere. So the Earth is here at the center of this plot, and just gives you a sense of how variable the Earth's near space environment is. So this is the region of space that's dominated by the Earth's magnetic field, and the sort of bubble that we live in that shields us from the solar winds. The solar wind is coming from left to right, and it's hitting at the magnetopause here, which is the separation between our magnetosphere and the solar wind. You can see that as the solar wind waxes and wanes, the magnetosphere tracks it and contracts and expands as well.
What's the units on the axis?
So the axis is in units of Earth radii, which is roughly 6,300 kilometers. So on the nose of the magnetosphere is typically between 10 to 15 Earth radii ahead, between the Earth and the Sun, and you can see this long magnetic tail that exists behind. So all of the variability that you see here translates into variability that we see at lower altitude. So that's a very active area of research, is the coupling between what you see here and what happens at lower altitudes in the ionosphere. Of course, one consequence of that, where I've done some research in the past is at higher latitudes in the aurora. So going to a slightly different part of the ionosphere. This is imaging from a UV imager on NASA's Polar spacecraft, which is not functioning anymore. This was back in the early 2000s, late 90s, early 2000s. So this is far ultraviolet global imaging of the aurora, of the northern auroral oval, and you can see globally, of course, the aurora is distributed, sort of centered around the magnetic pole, but you can get a sense of how much structure there is just within that, and how dynamic that is. And this is tied directly to.
There's the big bright glow on the left. There's the natural illumination from the sun.
That's right. So this is all day glow here. The sort of the unstructured part. When we process these images, try to subtract that out. But of course,
sometimes you do, sometimes
you don't. Yeah, sometimes you do better.
Tell people about it, it gets very confusing.
Right. So, but the contribution from the aurora is seen here in this, this sort of oval region. You do your best to try to subtract out the background, but sometimes it sneaks into the images.
Does that always maintain a constant radius? It looks like it is.
No, it actually expands and contracts. Of course, when auroral activity, when geomagnetic activity increases, it expands. Actually, both poleward and equatorward.
It looks like matting is like it's like an Indian distance.
Right. It's hard to tell quantitatively from this type of projection, but typically during a geomagnetic storm, when the entire magnetosphere is disturbed, the aurora tends to move equatorward, but it also does expand out in the other direction as well. So one thing that Patrick shared with me when we were talking about this presentation was some of the quantities that are used by the amateur radio community to get a sense of the level of disturbance in the ionosphere and the geospace system. And so one thing that Patrick showed me was this display from the QRZ.com website, which I guess is a fairly common resource for the amateur radio community. So we thought it might be kind of useful to maybe walk through a couple of these things and sort of discuss what what some of these quantities mean, where they come from, and how useful they are. This is actually the display from today. I pulled this morning, so this is all what's happening right now, essentially. So just kind of going through some of these. Of course, I'm sure most of you have seen this. So this quantity here, what's called the solar flux index, that's what I more commonly know as the F107 index. This is a solar radio emission at 2.8 gigahertz. It's a radio emission that originates in the lower part of the solar corona, or the transition region between the lower parts of the solar atmosphere and the corona, and it's measured by this radio observatory in Canada. It's a good climatological metric of solar activity, because it's been measured since 1947. So it gives us a long time record, and this parameter is basically used as a proxy for solar activity. How active is the sun? So you look at this one number, and it gives you some sense of that. Actually, it doesn't have physical units, but it's mostly reported in terms of this solar flux unit for convenience.
How dependent is solar radio emission on frequency, both in terms of average and in terms of variation? Pretty much, if it increases it at one frequency, does it also tend to increase at another frequency? Or it's wildly independent?
Right. So I'm not as familiar with the radio portion of it, but I do know, in terms of the extreme X-ray through the visible portion, the X-ray through the EUV portion is highly variable through the solar cycle, whereas the visible portions of the sun through the infrared are a little more invariant. So most of the variation that we see from solar max to solar min is the short wavelength portion of the solar spectrum. I was actually looking for a plot. I know there's a plot somewhere that shows that, but I wasn't able to find it. So this is just a long time record of the F107 index that I pulled this morning. Just shows the peak of the last solar cycle through the previous really long solar min, and now coming back up. You can sort of see some sense that maybe we're going through this sort of double peaked solar cycle now. So this next one is also a fairly common metric, the sunspot number. This is essentially accounting through slightly. It's not quite as simple as just counting the number of black spots on the surface of the sun that you can see from the ground, but it's essentially another metric of the level of solar activity, because as solar activity increases, the more sunspots there are. So sunspots are regions of the solar photosphere that are associated with emergent magnetic flux, magnetic fields emerging from the sun, which tend to impede convection on the solar atmosphere, and so the material there on sunspots is relatively cool relative to the surrounding portions of the sun, so they appear darker. And again, this is another metric that is commonly used to kind of quantify the level of solar activity. And so we see sunspot number here through our current solar cycle. You can see the solar max is a little wimpy compared to the last two.
That was a long, cycle 23 was long, wasn't it? Because I remember hearing that the solar cycle wasn't starting or something.
Yeah, it was a fairly active time. I was just finishing graduate school right around people measure their careers in terms of solar cycles. So I was sort of a solar max grad, and now that was really exciting to be in grad school at that time, because there was a lot of stuff going on. And right now we're kind of still waiting for things to really happen. and so you can see that most of the predictions for this current solar cycle are showing it to be a fairly benign one. This other index, this index A here is this geomagnetic index. I've actually never really, I've never really found it to be of common use in the community, so I kind of skipped that one. But this one's fairly common. The K index is essentially a measure of geomagnetic activity. It's a average of magnetic field measurements taken at mid-latitude stations, and it's used as sort of a kind of barometer of how active the geomagnetic field is on any given day, on a scale from 0 to 9. It's kind of a logarithmic scale, where it's sort of semi-useful. It doesn't tell you a lot in terms of the actual physical details, but it's sort of, you know, about as useful as looking out the window on a given day to see whether it's going to rain.
You could think of that as sort of being how much jitter there is the way your compass is pointing.
Yeah.
Okay,
Essentially.
figure that one out.
Yeah. So this, you know, this is the KP index for this week. Right now, things are relatively quiet. Let's see. This one is a little bit more useful in terms of understanding, getting a sense of what's happening in the lower parts of the ionosphere, the GOES X-ray flux. So this is the solar X-ray flux measured in two different passbands, sort of a longer and a shorter wavelength passband measured at geosynchronous orbit on the NOAA GOES. And X-rays deposit their energy at lower portions of the ionosphere, mostly in the D region. So this gives you a sense of how much ionization there might be in the D region.
So what's the C 1.1? Is the 1 and the 1 the two different passbands?
Yeah. So this is the display. If you actually go and look at the data. There are different categories, and I can't remember what the origin of these are, but different categories of X-ray flux. So C would sort of be a moderate level of X-ray flux. X, of course, being the highest level. So this is where we are today. That
C 1.1 though, 1.1 is.
Yeah, I can't remember how that number is relates to. I sort of think of things more in terms of the actual physical units, but that's one metric that I'm not as familiar with. But say that somebody tells you there was a C-class flare, or an X-class or an M-class flare. That's kind of what they're referring to. Is sort of the general category, the strength of the solar X-ray flux. This other one, the 304 angstrom flux. This is a fairly strong EUV emission line from the sun that originates in the chromosphere. It originates in plasma that's at a temperature of roughly 50,000 Kelvin. So, which is actually not that hot relative to other parts. I mean, the solar corona is about 1 million degree plasma, fairly tenuous plasma, but super hot nonetheless. This emission originates from helium ions, and it's again this UV emission is a major source of the photoionization here at Earth. So I think this is one of the more useful ones to tie to the ionosphere here, because this emission line is a fairly significant source of ionization in the upper atmosphere. And this is what the sun looks like at the helium-304 line. These are images from the Solar Dynamics Observatory. This is from yesterday. I tried to pull something fairly fairly recent. So you can see that the 304 line picks up a lot of all the more sort of mesoscale current loops that occur associated with the active regions on the sun. So these bright spots out in the visible would look as like a sunspot. But as you go down into UV, you can see that there's a significant amount of structure when you look at other wavelengths. So.
Maybe I'm going to stop you for a second so I can change pace and
Oh, sure.
give you a chance to have a drink of water.
Okay.
Okay, you're on.
Great. Right. So picking up from where we left off, this is sort of tying back to one of the space weather parameters reported in one of the data sources that I think is available to the amateur radio community. This helium-304 line, and I just wanted to show what the sun actually looked like in that emission. Let's see this other one. There's this auroral index here reported in that field. I don't find this. It's about it sort of falls in the category of this KP index. The way I understand that this index is created is that it's actually taken from low Earth orbiting satellites that make energetic particle measurements that kind of delineate where the auroral oval is along a given satellite track as it cuts through. And then they use those measurements to extrapolate the entire auroral oval. And then they use that to compute this, basically how much energy is being dumped into a particular hemisphere. Yes.
Okay, I'm going to win the prize for the dumb questions, but how high can SFI go? And what's the estimated SFI for the 19th century event that zapped out all the...
the Carrington event?
Yes, the Carrington event.
Yeah, the F-107, I think, typically goes up. I don't know if there's an upper bound to it, but I think modern records typically goes up to maybe like 200 or 300.
Mm-hmm.
Yeah.
And the Carrington event, what would that be?
I don't remember what it would have been.
I mean, obviously we don't know, just guessing.
Right. Yeah. It probably would have been maybe 300-ish, I think.
Okay.
Just as a total wag.
And is there ever a CME such
Mm-hmm.
that it destroys satellites? I mean, not physically, but just makes it, okay, forgot that one.
Yeah. So in the sort of recent history, there have been some coronal mass ejections, and I'll sort of touch on this a little bit later in the talk, that have driven other phenomena, like associated with CMEs are also solar energetic particles,
Mm-hmm.
so relativistic electrons and ions, mostly protons. And relative to satellites, those are fairly dangerous because those are fairly high penetration events, and they can cause things called single event upsets in satellites. There have been examples of telecommunication satellites that have been rendered inoperable due to these things. I don't know if they've been associated with individual CME events, but typically when those occur, they're typically synonymous with a coronal mass ejection interacting with the Earth.
What's the lowest the SFI would be? 100?
If we go back and look at that,
By the way, I remember reading a recent study where somebody looked at when satellites failed, and there was definite correlation between when satellites failed and when the solar activity was higher. So you can't really blame it on any one satellite. failing on that, but
Oh, sure,
definitely
yeah,
a
I mean, you
factor.
could, yeah. So these solar energetic particles, they're very short timescale events. Yeah, even coronal mass ejection happens on a timescale of a couple days. Once they, it's about the timescale of a geomagnetic disturbance at Earth. So the reason it's hard to make these one-to-one associations between. That's one problem that the space weather community has is making a real strong association between an actual event on some piece of hardware and associating that with the larger weather, the bigger scale picture of the weather that's happening in space at that given time. But back to your question. F10.7 index for solar, this is about the lowest solar wind that we've experienced in recent history, so that
It's
10.7 is about 50, 60-ish. This is a 27-day running average, so an average over one solar rotation. And you can see the values here, in some cases getting up to high 300s. Or mid 300s. Okay, so this auroral index again, I personally don't find it particularly useful because it's fairly coarse. I think NOAA is actually switching to a different forecast product now. Where they're actually starting to incorporate more imaging as opposed to a single satellite pass at one longitude and then trying to extrapolate out. I think they're starting to use a little bit, incorporate more imaging that is a little bit more representative of the actual distribution of the auroral oval at any given time. You remember from that movie that I showed that there's fairly small scale structure distributed among this oval, but for a single number, it's hard to kind of collapse that into a signal number, but that's kind of where it is. So these last two, I think, are a little bit more useful because they're more physical to me, so it's easier for me to understand. This is the BZ component. So this is the north-south component of the solar wind magnetic field, and this is a fairly important parameter. Because it's the more southward pointing that magnetic field component is. So this is the component that's perpendicular to the ecliptic plane. The more strongly south it points, the more efficiently the solar wind can couple its particulate and magnetic energy into the Earth's environment. The Earth's magnetic field at the equator is directed up, and if you have a strong magnetic field coming in from the solar winds, there's this process called magnetic reconnection, where there's a local cancellation of that field, and there's a stronger degree of energy coupling between the solar wind and the Earth's environment. So the more negative that number is, the more disturbed things are going to be typically at the Earth.
What date is this one?
So this is from today. Yeah, this is where it pulled from.
Well, I'm looking at it right now, it says it's 0.8 BC.
Right.
You're 3.8.
Oh, this is from this morning. So.
Oh, okay, so
Yeah.
it's 0.8
Right.
now. Okay, got it.
So the next one, this coupled with this one, I think give you a good sense of how active the solar wind is. This is the solar wind velocity in kilometers per second as measured by the ACE spacecraft. The ACE spacecraft is sitting at the L1 point, the L1 Lagrange point, which is about 1.5 million kilometers between the Earth and the Sun. It's a stable gravitational point, so you can send a satellite there and it'll basically park itself around a fairly stable orbit. It's a nice place to make measurements like this because it doesn't require a lot of energy to park a satellite at that location, and you get a sort of upstream monitor of the stuff coming in. There's a lot of stuff going on here, but the two things that I just described are shown here on this top panel. So this is the strength of the BZ component is this red trace. So this is in units of nanotesla, minus, which is a unit of magnetic field, minus 30 to 30. The other parameter is shown here. It's the solar wind velocity from 200 to 1,000 kilometers per second, and this is on a daily. So each major tick mark here is a day. So this is what we saw. These are measurements from today and from the last about week or so. You can see sometime on the 6th. So what was that? Earlier this week, over the weekend, I guess, that there was a ACE measured some disturbance in the solar wind. I don't know if this was associated with the scenery or not, but you can see typically what happens is you see this strong enhancement in the magnetic field, and then following that is this higher speed plasma that's plowing through the sort of ambient solar wind. So this is the type of display that we typically look at when we're trying to gauge what to expect at Earth in terms of space weather and disturbance. So we look at parameters like this, preferably as far out as we can to enable some kind of forecast capability. So anyway, that's basically all I had. I hopefully gave you some flavor of. This was, of course, a fairly high-level survey of space weather in general, but hopefully it gave you some flavor of what we see on a number of distance and time scales in terms of ionospheric and solar variability.
Thank you.
Yeah.
Thank you.
Thank you.
Very cool. That would be very useful, and I'll have to go back over it, but in particular your slides about using that QRZ widget, and just looking at that and knowing what to expect.
Yeah.
That would be great.
I mean, I guess it really depends on your own personal interest and the questions that you're trying to understand, and if there's a particular aspect of the ionosphere that you're wanting to get a better sense of. Some of these will be more useful than others. Personally, I think the X-ray flux and the speedsy and the solar wind velocity are a little bit more. For me, it's easier to understand because they're tied to some physical. That's an actual measurement. It's not some index that's been kind of run through a black box, and there are actual physical units on those. And so.
Did you get the definitions from the QRZ.com website?
I just for the purposes of understanding what they were referring to.
Did you get that from PRZ? I mean, SW. Aren't those your own?
Yeah. So the definitions are.
That's what I
my
need.
own.
I publish it on our website over in Alexandria for Radio Club.
Right.
I'm going to publish his slides on our website, so you'll be able to go back and get them.
That'd be wonderful.
Yeah.
But I'd like to know so I can know what the value is, like you have there.
Right. So the units on that would be.
The units, and I keep one of the units and values.
So it would be kilometers per second.
Yeah.
Garden variety solar wind on a quiet day is kind of 400 kilometers per second. The solar wind associated with the coronal mass ejection can be about 1,000 kilometers per second. So it's about the upper and lower bounds is what we typically see. So coronal mass ejection, once it's detected on the sun, so by imaging means, typically takes, depending on the velocity, takes anywhere between 1 to 3 or 4 days to reach Earth if it's Earth directed. There was one that was studied in great detail that I think would have been the largest space weather event ever recorded on Earth, but it was not Earth directed, but just judging on the velocity and the magnetic field that was estimated associated. It would have been one of those sort of 100-year storm kind of things, and I think that happened sometime last year.
How directed is any particular coronal mass ejection?
They happen at every sort of solar longitude. They go off all over the place.
And do they have? I mean, are they fairly focused, or are they just kind of broad?
It kind of depends on the latitude in which they originate. Because there are active regions that are distributed across some range of latitudes on the sun, these coronal mass ejections can start. Go back to they kind of happen all over the place, and they can occur at any point during its solar rotation. So sometimes we observe them, and you can see. You can see them very clearly in terms of its loop structure, like this. You can see a few of them. So a burst like this or a burst like that, you sort of see the loop structure. The ones that are Earth directed, they're actually called halo CMEs because now you're looking at it from face on. And so basically, when that occurs, you basically see this halo coming out from behind the disk. So halo CMEs are the ones that are typically Earth-directed. That's when we know that. So all the ones that you see here are coming off of the limb. They're going off in whatever direction.
Is it the angle of incidence of impact of one of these flares on Earth that determines the relative
Yes.
North-south attitude of the magnetic flux?
Exactly. So the orientation. So that's why that BZ component is really important to know, is because basically kind of the angle of incidence of that CME once it hits Earth can make a particular CME of kind of a dud, or can make it fairly powerful, depending on its relative orientation when it actually interacts with the magnetosphere.
Do those things rotate in magnetic moment or anything like that? Do they hit at a random orientation?
They kind of come in a random. It's systematic in the sense that there's a fairly organized structure to it. So the loop that you see here, these bursts that come out, the loop portion is representative of a magnetic field structure. So it's kind of a magnetic bubble, and depending on where it's coming out from the sun, it's going to carry whatever magnetic field is associated with that active region out along with it. Magnetic field is trapped in plasma. It's kind of frozen in, and its orientation is going to be preserved in that plasma as it propagates out somewhat, sort of the zeroth order. And so typically, with a fairly high degree of energy, it's plowing through the ambient magnetic field ahead of it, and so it actually creates a shock. And there's a fairly complex set of interactions that occur along that shock. So it's kind of super sonic, I guess, if you will, in some cases, where it's actually traveling faster than kind of the magnetosonic speed at that sense sometimes. Which is to say that the orientation of that magnetic field can vary significantly. So if the CMEs that carry a strong southward directed magnetic field are the ones that typically are responsible for a higher level of geomagnetic activity. There are ones where the magnetic field is oriented the other way, and statistically speaking, I think researchers have found that the bang that they produce at the Earth is not quite as strong as the ones with southward BZ.
That easy measurement is done only at the ACE spacecraft, which is like 15 minutes, an hour away or something?
Right, which is a real issue if you're trying to forecast something with any kind of useful timescale.
So is there any hope of like measuring the easy?
So yeah, that's kind of the holy grail of solar research, is to be able to do some kind of remote sensing measurement of the magnetic field in the corona before it leaves, because then you have some sense of what it was at t equals 0 when the clock starts. The other problem is you can't see beyond the limb of the sun from the Earth, obviously, which is why we launched stereo, to get some vantage point, kind of perpendicular to the sun-Earth line. And the degree in which you can forecast any of this is really dependent on your ability to see as much of the sun as possible, and to be able to detect these things as early as you can. Otherwise, you're kind of stuck with nowcasting, which is not, obviously, it's as useful as looking out the window and to see if it's raining or not.
Are there any plans for the solar observer satellite on the opposite side of the sun?
Not that I'm aware of currently. There are missions that are being proposed to put an observatory at a different Lagrange point. So I mentioned L1, which is on the Sun-Earth line, obviously closer to the Earth. There are two others called L4 and L5, which are.
That's where stereo is, isn't it?
That's where stereo is roughly. That's where it was toward the beginning. Stereo actually precessed. So at one point they were 180 degrees apart, kind of perpendicular to the sun, and they actually went behind the sun, and now they're coming back. But the L4 and L5 Lagrange points are, I think, 60 degrees.
Behind.
Yeah, that's right. And so that would be a really great vantage point for making a lot of these observations, because you're getting a little bit of looking beyond the limb of the sun, from what you see here on Earth. So there have been some proposals to put a space weather monitor out there as well. Some of which actually, just as an aside, would incorporate a solar sail to do station keeping, but nothing concrete or in the works as far as I know.
You mean like to hold it in place?
Yeah, to sort of keep it from drifting. I think the L4 and L5, I think they're stable orbits, but
Yes, L4 and L5 are stable, the others I think are unstable.
right. So, but there are other ideas like using solar sails for station keeping out, not quite at L4 or L5, but sort of in that vicinity. So you would use the solar radiation pressure to counteract the tendency for it to want to fall back toward the sun and the Earth. So there were some ideas and some
Can you do
exotic than others.
monitoring CubeSat?
Well, some of the proposals to go to L4 and L5 would be to use CubeSats, which I sort of find a little bit hard to believe. But we actually proposed one as a demonstration mission called Mini-Core, which is to put one of these on a CubeSat and send it out to L5. There are ambitions to do that with CubeSats, but I don't know that it'll happen. No one's demonstrated that CubeSat could operate at an operational level at those distances. So I mean, we have a lot of experience using CubeSats in LEO, and they're doing a lot of great stuff. We actually just recently launched a couple payloads on CubeSats to make neutral atmosphere measurements on Air Force satellite STP something. I can't remember the name of it. this is another group in my building. But so far, nobody's been able to demonstrate the performance of CubeSat for the route. But I think that's kind of the next frontier of missions. Not necessarily because there are a lot of things that might fall out of that in terms of miniaturizing technology and making things more efficient in terms of the usual parameters like size, weight, and power. So even if it doesn't happen, I think that in terms of the mission design, I think a lot of good things could happen as we go that direction.
Okay, one more question, anybody?
Are you guys able to predict the future of radio waves or disturbances? Like the weather man predicts how accurate or are you guys able to predict?
So there are a couple products out there. There's one product out there called the S4 index, which is a scintillation index. People that event that I mentioned about the SATCOM outage over Afghanistan prompted the community to come up with a model to try to predict the occurrence of these plasma bubbles in the equatorial and the latitude.
How did they know that it wasn't equipment failure? I mean, it just seems to me, let's blame the CME plasma bubble. It wasn't the low bid contractor. I mean, was that ruled out?
I don't know the details of the investigation, but I think based on the fact that there were other aircraft in the general theater of operations where factors like multipath and their lines of sight to a particular satellite weren't necessarily through that plasma bubble, that didn't experience communication outage. That sort of, I mean, it's difficult to say definitively that that's what the cause was, but in the forensics, I think the conclusion was that may have been a strong contributing factor, but I haven't seen anything to say that there were other factors involved in that incident that caused it to not end well. So,
isn't it the A or the K index that shoots up to like 50 or 100 if there's a major disturbance? I forget. Is it the K or the A index?
I think that's the A index.
Okay.
I didn't really talk about that because I actually don't think it's very widely. I haven't really seen it used very commonly. And in fact, I had to kind of NOAA doesn't even actually display it on their space weather website anymore. So I didn't really go into that because I hadn't found it quite as useful. In fact, I had to I think there are resources that talk about the A index don't exist anymore as far as I could tell. It's not on it's not presently shown as a product on their website. But the K index or KP ranges from 0 to 9 with a fairly coarse gradation between them. And it's a little bit like the Richter scale, where it's some quasi-logarithmic. So the difference between 0 and 1 is not quite as significant as the difference between like 5 and 6 and 7. So KP of 9 is fairly rare, but fairly high level of disturbance typically corresponds to KP in the 5 to 6 range, 7 even. So again, KP is one of those things where you glance at it and then you go look at other data that gives you more information on what's actually going on. It's kind of a barometer for what's happening on a given week per se. So
okay, I'm going to call it. You've been talking for an hour and a half now. You've been very generous with your time.
Thank you very much.
Well, thank you for inviting me to come speak. It's always good to connect with a community that is, maybe tied into the more user end of the community to get a better sense of where the interests are.
And I don't
what's
think-
what's useful. So it's
Yeah.
helpful for me too.
I don't think any of us has seen an explanation of the science behind it tied to the language that we use and showing us, you know, in the bands that we use. So thank you for taking the time
Or explaining what
to
those numbers
research
mean.
that. Yeah.
Oh, sure.
Thank you very much.
Sure.
One of
You're welcome.
our last